As it finishes its warm-up, we'll be recording. Now, why is my... Oh, there we go. All right. Couple things before we get started. Tuesday, we have what they call a planning hearing over on the Birmingham campus at 10 o'clock in the morning. I'm required to be there. I've been working on it for a while, for months now, but I'm still waiting to get some stuff from some of the instructors. And I talked with one today, and he had forgotten to send me anything. So he's going to get it to me tomorrow, which is Friday, which isn't going to give me very much time to do very much. So, I've got to email my first class, my morning class for Tuesday, Thursday, because it looks like now, because he's not going to get me the stuff until the weekend, and I won't have the facilities to get it all put together, I'll probably have to go to the Birmingham campus first thing Tuesday morning, and put it all together then, which is a pain, but I guess I've got to do it. So, what that means is Tuesday I will not be on campus until right before class time. So that means if y'all are here at 12 and I'm not, hang tight because I'll be here. This is next Tuesday. Okay. Our hearing is 10 to 11. But then the one that follows us, I've got to be there for part of that. So I hope to be able to get away by 11:30. So I'll be here by 12. Okay. So I won't have any office hours that morning. No 10 to 12 office hours, but I will be here, hopefully in time for class. Now, like I said, if I'm not, hang on, I'll be here just as soon as I can. Okay, and then the rest of the term, I think we're okay. And guess what? We only have class next week, okay? Because the last day of class is Monday the 31st. So our day we would normally be back would be the following Tuesday. That's supposed to be the first day of finals. In fact, that's when the first day of finals is. So let's talk a little bit about that. Now, number one, y'all have been great about getting stuff in, and I've tried to get stuff back to you as you get it in. But on next Thursday, I'll be returning everything to you. That's all the labs and all the tests. Not your research papers. I have to hang on to that because they want samples of student writing periodically, so I have to hang on to that. But other than that, I'll give you all your labs and tests back that I haven't already given you by then. So that means that next Thursday is the last day to turn something in. So get everything into me today, Tuesday, or Thursday. All right. Then on the following Tuesday, the final exam, I think you'll find it's going to be very short, very easy. You can use formula equation sheet just like always. It may actually be in two parts. I'm guessing it will be. The first part will probably be the last chapter we've done, and the second part will then be the final exam, the comprehensive part. Neither one of those will take you 30 minutes to do. So, since we have an hour and 50 minutes, it's not this coming Tuesday, but the following Tuesday, final exam, why don't we have pizza or something? Is that okay? Anyone have any dietary restrictions on pizza? Can everybody eat? What pizzas do you like? Pepperoni? Okay. How many do you think we need for the 5 of us? Myself and y'all, the 4 of you. She wanted 4 pizzas, huh? Okay. How many do you think? Second?
2 large.
2 large? Okay, both pepperoni, or you want a different kind? You want to like anything other than pepperoni? Second?
Meat lovers and pepperoni.
Meat lovers and pepperoni, okay. All right, we'll try to do that. It won't be this Tuesday, of course. It's going to be the following Tuesday. Okay. All right, we'll try to do that, and then once we finish that, I'll return anything else to you that you may have turned in on the previous Thursday that I got graded, and I'll get that back to you, and then we'll have the last chapter test and the final. Or at least that's how I'm thinking it can out. All right. That should be everything. Any questions on anything we've done so far? Okay, when we finished chapter 19, we did the lab, and I gave you a take-home test, so y'all are working on those, I take it, unless you've already turned it in. Okay, so today we're starting chapter 20 from scratch. So if there are no questions, and this is a really pretty picture, the one in your text is very similar to it, a little bit different. This is, they don't tell me where this is, though. They say weathering and erosion tend to sculpt or wear down the land, sometimes leaving behind rock structures of more resistant rocks, such as those you see here. And here's the source, but it doesn't say where this is. Pretty impressive looking area, okay? So, the last chapter was building the Earth's surface. And what were some of the ways we built the Earth's surface? Say again? Okay, mountain ranges were formed. 3 types of mountains you have out there. What are they? And the various subgroups. Yeah, fault block mountains, folded mountains, and you said it. Say again? Volcanic mountains, exactly. Okay? So those are the 3 major kinds that we do, and the Earth's surface is built that way, usually from below, stuff coming up. Now we're going to shape the Earth's surface. Okay? And that's what this chapter is dealing with. The core concept here is in your book. The surface of the Earth is involved in an ongoing process of destruction and tearing down of higher elevations. Now, in your text somewhere later in the chapter, you're going to see a picture similar to this, maybe exactly that picture. Do you know what that is? A waterfall. Okay? You may not know where it is, do you? What would you say sort of the color of that rock right there to be sort of the color of that stone? Sort of. What color?
Brown, yellow.
Say again?
Brown or yellow?
Yeah, okay, yellow. That stone is yellow. Hint. Yellowstone. That's the, I don't know if you're quite in the park yet. I think you are, but this is the upper falls of Yellowstone River. Now, you may find it hard to believe, but at one time, the land level was something like this. But this water came through and found the weakest and the softest and the most easily eroded soil and started tearing away at it. Okay? And all this that's in here was once soil. It's been washed away. Okay? And we'll talk about this later. This is the upper falls, somewhere downstream. There's another set of falls, and somewhere downstream from that, there's Lake Yellowstone. Okay? And that is a huge crater lake, as we talked about before. A huge crater lake. I never would have guessed it just looking at the lake, because it's so big you can't see that. From above, I think you probably can. So, pretty incredible how much soil over thousands of years probably has been eroded away. The first major topic here is weathering. Okay? In your text, they actually have one that's weathering, erosion, and transportation. Okay? And then we'll break those down and do weathering next, and then soils, and then erosion. And I don't think they do a section they call transportation, but that's part of all of it. Okay? So that's kind of the setup here. Almost seems like they're a little redundant in some of their topics that should be, I think, subtopics. So what do we mean by weathering? Weathering is something. Slow changes resulting in the breakup, the crumbling, and other destruction of solid rock. Okay? Because all rock, and guess what? All soils, all of the hard surface of the earth was at one time igneous rock. Okay? It was rock, and that was all igneous rock. So, obviously, it's been changed over time, and part of that change process is done by weathering. Now, it includes three major types of weathering. The book loves groups of three, don't they? Okay? Physical weathering, there will be another name for it you'll see later, mechanical weathering. Same thing, physical weathering, mechanical weathering. Chemical weathering and biological weathering. Now, they call them processes here. The book says precious little about biological. I'll probably supplement that a little bit. It focuses mostly on physical and chemical, or mechanical and chemical weathering. Okay? All this contributes to what we studied in, three chapters ago? The rock cycle. Okay? Because, like I said, all rock started as igneous rock, and then the weathering is what basically breaks that down into both chemical and plastic pieces, and those are reformed in sedimentary rock. Those may undergo more pressure and temperature changes and stuff like this and become metamorphic rock, but so the igneous rock could have become metamorphic rock, but they all wear down and go through that cycle over and over. If you remember, part of the rock cycle was sediments all around there, you know. So sure enough, that's part of contributes to the rock cycle. That's not all, folks. If we didn't have this weathering, there would be no life on the planet. Why? Or not life as we know it. Because without soils, we don't live. And where do soils come from? The weathering of rock. So, weathering is not necessarily a bad thing. It can be, but generally we benefit from it when it forms our soils and we don't lose those soils. It also contributes to the movement of rock materials over the Earth's surface. And we'll see some of that too. Incorporated in weathering, in these processes, and in this, is erosion. Erosion is the process of physically removing the weathered materials. Now, actually, when I studied as a soil scientist, and we used to talk of erosion as having two parts. The first part is they call detachment, and the third part is transport. So both of those are involved here. The physically removing of weathered materials. You have materials there, you have to separate it from the existing material, that's the detachment, and then you have to get it out of the picture, that's the transport. So erosion contains both of those sub-processes. The process of physically removing the weathered materials.
Is that what a mudslide is?
Exactly. Mudslides, landslides, we'll talk about several, and dust bowls, I mean, all that is forms of erosion. But you hit some of the big ones right there. All right, let's go first to what we were calling on the previous slide, physical weathering. This slide calls mechanical weathering. Okay? Is this a subtopic or? I think this is just part of this. Mechanical weathering. Now what this is, they call it mechanical here, and then say the physical, so they go hand in glove. The physical breakup of rocks without chemical change. The physical breakup of rocks without chemical change. And they give several of these disintegration processes. And frankly, to me, these are sort of, they do happen, they are important, but they're sort of on the minor side of things. The first of these they call wedging. Now, that's not something you do to your little brother or something like that. What we mean here by wedging, wait, y'all aren't supposed to know about that. What's this laughing, huh? Okay. Now,
will sinkholes fall into that?
it is part of the process. They're usually, now we've talked about there's two different kinds. One is a physical process and one's a chemical process. Most sinkholes, I think, are more, I don't know, I want to say more chemical, but I think we talked about the ones back here on Powder Plant Road and those kind of areas. I think those are largely physical. This isn't what we're talking about here, but it is talking about physical weathering. So, yeah, and my guess there is that James may be here. Yes, he is. Okay. Perfect attendance again. After a brief break of non-perfect attendance, we're back again. Yeah. My guess in Florida, a lot of those sinkholes are chemical. I don't know that for sure, but I'm guessing. Because I think Florida has a lot of limestone, carbonaceous materials, and even others that when they're exposed to especially acid rain and things like this, they chemically weather and then they get wet. Okay? Some of the things back here, from what my understanding is underground water washing things out, which is probably mechanical or physical weather. Roads that have sinkholes in them, I'm wondering if sometimes the sewer system is so old and decrepit, the storm sewer, the waters that's rushing underneath is eating away. That might be physical, but it could be chemical too. You'd have to sort of study each individual. What they mean here, and again, these to me are fairly minor, but they certainly do happen. What do they mean by wedging? Well, over time, all rocks will, for some reason or another, get little tiny, sometimes hairline cracks in them. Okay? Places where the bonding just isn't super strong. And when that happens, water finds a way to seep down into those cracks. Okay? Water goes into the cracks, and then not so much here, but it can happen to a small degree here. But in colder climates, then in the wintertime, that water that's in there, water is one of the, if not the most, one of the strangest compounds on the surface of the earth. It has so many fairly unique properties, and yet it's the most common material on the surface of the earth. 60-70% of the Earth's surface is covered with water, okay? And yet it's a weird substance. Number one, what's its chemical composition? I think everybody knows it, right? H2O. What does that mean? 2 hydrogens, 1 oxygen. Exactly. Yeah. And oxygen has a molecular weight of 16. Hydrogen, 1 each. So 16, 17, 18. Molecular weight of water is 18. I do not know of any molecules with that small a molecular weight that aren't gases, except for water. It's a liquid. Okay? That has to do with the hydrogen bonding. Remember when we were filling that container and it went over the top? That surface tension, that's to show that strong hydrogen bonding. That water was over the top of the beaker, and yet it still wasn't spilling because it was hanging on to one another as tightly as it could. Okay, that's why it's a liquid. Okay, that's one strange feature of water. Another one, thank goodness for this one. Water is one of the few, if not the only substance. Now, most things, what happens when you cool them? They shrink. Okay, because the molecular activity slows down, it's not as strong, they tend to shrink. Okay? And certainly when a gas goes to a liquid, that reduces volume. And most things, when it goes from a liquid to solid, that reduces the volume, except water. What happens to water when you freeze it? It expands. People who have had burst pipes know that for sure, okay? Water expands when you freeze it. Nothing or hardly anything else does that. Water does it. And the reason is water, in its hydrogen bonding in the liquid state, they just slide past each other but stay really, really close, the molecules. But when it gets into the frozen state, it goes into this crystal lattice, which actually expands its structure. So water expands when it freezes. So that water that crept down into that hairline crack, then in the wintertime when it freezes, it expands. How strong is that bonding in water? Pretty strong. It will actually push the rock further apart. The next year it's a bigger crack. More water gets down, it freezes, pushes it further. At some point, it breaks the rock. Okay? So that's wedging by frost. Now, tree roots do a lot of the same type thing. And not just tree roots, grass roots, any kind of roots. In fact, have you ever noticed, if you're out in the wilderness or wild areas and stuff like that, a rock that's sitting there, big old chunk of rock that's exposed, has these little patches of stuff growing on it, right? From those little lichens, that's one type of stuff that goes on, to trees, grasses, anything, what they do, where is the activity of a plant? The roots. That's why activity is happening in the leaves too, but the raw materials, a lot of the raw materials for that come from the roots. Now the roots themselves don't do that much work. The roots basically hold the plant in place. But at the end of every root, or just about every root, there are smaller roots and smaller roots until finally you get down into what they call root hairs. Okay? They are so incredibly tiny, some of them aren't even visible. Okay? Very tiny. That's where the action goes on. Because they are so small and their walls are so thin, minerals can transport and water can transport back and forth across those that membrane. Okay, relatively easily too. That's where the tree takes up all the nutrient it needs. That's where it takes up all the water it needs. But that's also where it secretes some stuff. We'll talk about that in just a second. So these little root hairs, they like to get down into places where they can get the nutrients. And sometimes that's the little crevices and cracks. Because those rocks sometimes contain some pretty good nutrients. So they get down in there, crawl their way in, work their way in, grow into them, and then later they grow into bigger roots, and they send out their root hairs, and then bigger and bigger, and after a while, the tree roots have done the same thing by wedging. So you think you came up with the idea? No. Water and tree roots have been doing it for millennia. Okay. Now, let's go back. I said those root hairs take in stuff, they also secrete stuff. Those clever little devils, you know what they secrete? An acid. And what does that acid do? It eats away at whatever is around there, dissolving it, and then when they get the nutrient they need, they grab it up and take it up to the plant. So not only do those root hairs wedge, those root hairs also make it bigger by acidifying, which is a chemical process, not a mechanical. And all of it's a biological process. So these things work sometimes all at the same time, hand in glove, supporting each other, whatever. We're talking mostly here about just the root hairs going in and growing and pushing apart the things. The other type of disintegration process they mention here is exfoliation. And sometimes ladies do this, don't they? What does that mean? You're too young to know. Maybe you've heard your mom or grandma talk about it. or your wife or somebody else. What does it mean to exfoliate?
Like to remove dead skin.
Exactly. Remove those outer layers of dead skin, leaving us in soft. Yeah, that kind of stuff, right? Well, rocks do that too, but not intentionally. We talked about, in fact, you even mentioned, I think it was Brian, mentioned the mounding that sometimes happens. Use the correct term, I can't think of it now. Dome, yeah. The dome rocks or hills that are forming. And what happens with them, as there's pressure from underneath coming and pushing things up, of course, what happens to the surface? It was flat like this, and now it's got pressure from above. What's happening? You're spreading it apart. And where you spread it apart, it fractures, and the outer layers come off. That's what we call exfoliation. And you have this, and these are slow processes, but they're still happening, and it spreads that and loses some of the strength that binds it together, and then it exfoliates. So that's exfoliation. Reduce pressure from above, increase pressure from below, the fractures cause expansion, and then maybe rainwater can get in there. So, again, these can work together. Okay? So that's the exfoliation process. As you might guess, when I drive down the highways, I'm always looking at the road cuts. Because the road cuts can tell a story. The history, you can see layering, you can see faulting, folding, you can see lots of exfoliation. Because just about everywhere where they've done a road cut, look at the bottom and you see all sorts of stuff piled up down there that's exfoliated from up above or weathered from up above and deposited down in the ditch. Okay? Here's some tree roots doing their little number. You think tree roots can move a slab of concrete? You better believe it. Okay? That's not at all unusual. We have a big old white oak right by our driveway that is picking up and moving parts of the driveway. It's amazing. And I've seen up at Smith Lake and other places too, trees that look like they're just growing on rock. Okay? You think, how can it live there? Well, guess what? Underneath here, the little root hairs are secreting acid and dissolving and eating away at that rock. And that's a biological, chemical, and physical process going on. And they just hang in there amazingly. I've seen some places on the road cuts. It just looks like sheer rock going all the way up to the top, and yet there's trees growing up there. And they can't have more than that much topsoil, it looks like. However, they're finding ways to work down into the thing, wedging their way down and grabbing hold of whatever they can. So those are two types of disintegration processes under mechanical weathering. Okay, I don't know what they were planning, supposed to have put here. I don't see it here, but actually look at figure 20.1 in your text is an example of, and they said moving water. Sure looks like a dry area to me, but that doesn't mean it was always a dry area. Sometime in the past there was a lot of water that moved through there, and it ate its way through that rock. Really pretty amazing. That's Rainbow Bridge, it's called. Figure 20.2, piles of rocks and rock fragments around a mass of solid rock is evidence that the solid rock is slowly crumbling away. That solid rock that is crumbling to rock fragments is in the Chiricahua or something like that mountains in Arizona. By the way, the author's from Arizona State, so you're probably going to see a lot of Western pictures in here. And that's part of the thing that caused those things was probably exfoliation, like we saw here. Okay. says here, growing trees can break, separate, and move solid rock. The A picture there says, note how this tree has raised the sidewalk. And you know what? I think it was a different picture before. I think it was one like that before. Because this little girl walking down the thing, I don't see much raised sidewalk there, okay? But maybe there is at the seams and crevices, but I think they changed pictures. It's a great picture, but it doesn't seem to match the caption. And then the bottom one is more like the second one here. This tree grew into a tiny crack in the boulder, which became larger as the tree grew, cracking open solid rock. Okay? Unbelievable it can do it, but it can. Okay? Figure 20.5 is spheroidal weathering of granite. The edges and corners of the angular rock are attacked by the weathering from more than one side and retreat faster than the flat rock faces, and you get a rounded granite boulders, often which shed partially weathered minerals in onion-like layers. That's sort of what they mean by defoliating the layers. All right. That's most of the mechanical weathering. So any of those pictures I just talked about could have been what they meant to put there. Now let's look at chemical weathering. Mechanical is any weathering wearing away that didn't involve chemical processes. So chemical weathering are those that do involve chemical processes. And this is decomposition of minerals. That means taking things that were put together and held together chemically and reacting with those so that it tears them apart. They mentioned three here. They love threes, don't they? The first of these is oxidation. What do you reckon oxidation is? Okay, it's combining with oxygen. In one sense, this is how much water was formed, but in one sense, water is oxidized hydrogen. Okay? Oxygen is combined with hydrogen to form the new material. What's another very common, everyday type thing of oxidation? Say again? Rusting, exactly. That's iron that's been exposed to the air, usually with water acting as a catalyst. Water isn't really involved in it, it just makes it happen faster, and the iron reacts with the oxygen and you form iron oxides. Okay? Reactions with oxygen, and it produces, now, they mentioned the red iron oxides. There are more than one type of iron oxides. Okay? There's ferrous oxide, FeO, and then ferric oxide, which is Fe2O3. Okay? Because iron has two valence states. The FeO is the reduced form of iron oxide, and ferric oxide, Fe2O3, is the oxidized form, more oxidized form. That's the red iron oxide. Now, I can't remember if I told this story or not. I tell these stories in different classes. But about the hillside on the farm near the house where we grew up in. Okay. Georgia, Red Clay Hills. Okay. This hill is just obviously red clay. And we used to cultivate it. We have a permanent pasture now. But we used to cultivate it, and that hillside was just so red. Until you got down to the bottom, and it was gray. And I always thought that all the sand had washed off the hill and settled at the bottom, and that's what gave it the gray color, the organic matter mixed with the sand. Not necessarily true. That soil at the bottom was clayey also. The difference is, on the hillside, the water washed off of it, but enough was there to oxidize the iron to the bright red ferric oxide. Okay? But down here at the low area, it sat under water for a while, and then not as much oxygen could get to the iron, and that was reduced iron oxide, FeO, ferrous oxide, which is gray in color, bluish gray. Can anyone think of any other examples of red iron oxide and bluish iron oxide? What are these things right here? You see? Say again? My veins. And what color do they look like? Bluish. Now, if you can see an artery, thank goodness arteries are deeper, you can't see them, what color are they? Red. Guess what the difference is? The little hemoglobin molecules are the center of a hemoglobin molecule is iron, ion, okay? And when that iron in the hemoglobin picks up oxygen from the lungs, becomes ferric oxide, Fe2O3, bright red in color. Takes it to the muscles and the other parts that are using that. It uses the oxygen to oxidize the carbon materials that you eat for lunch and that kind of stuff, and then it leaves the hemoglobin with a reduced iron, ferrous oxide, which is blue. That's what's taken back to the heart or pumps it back to the lungs and gets red again. We do that all the time. In fact, if you ever nip go to get treatments and stuff, I always go in a vein, and if there's ever any bleeding, which occasionally will be a little bit, as soon as that blood pops out, it immediately turns red because it gets oxygen in the air and changes blue to red. You want to say something?
So it really is blue?
Yeah, the blood in there is blue, but as soon as it's exposed to oxygen, it's red again. Because that's iron, ferrous oxide turning back to ferric oxide. Okay? So it says red iron oxide. It's also bluish gray iron oxide as well. So that's oxidation. Now that's not in the thing, but you see all materials. Sulfur oxidizes. Carbon oxidizes carbon dioxide. That's what we do to our food. Just about any material will. Iron is the most common, and iron is all over our planet too. So yeah, there's oxides. Now, what do you notice? What's the difference between a piece of steel and a piece of rust? It's all iron. Actually, the rust has more things added to the iron, but that's a weaker thing. You have a rusted part, that's where it's going to break through, probably. Okay, so that's part of the chemical weathering. Okay. Now, a second type of chemical weathering after oxidation, and actually, when I say oxidation, I want to put / reduction, because oxidation reduction goes on. If one's happening to one thing, the other's happening to the other thing. Just like I said, when your body takes the oxygen out of the hemoglobin, and then it oxidizes the food that you just eat. So it was reducing the iron and oxidizing the carbon. Okay. So they go hand in glove, so I would say oxidation reduction. But they're focusing on the oxidation. The second of these is carbonation. It's a perfectly good term, but to me it's too restrictive. When you read the thing, reaction with carbonic acid. What is carbonic acid? Carbon dioxide dissolved in water. Have any of you drunk any carbonic acid lately? No one drinks sodas, huh? Okay, it's not a good idea to, but I have in the past. I've got one in my fridge right now. Now, some of those are phosphoric acid, but a lot of them, when you say carbonated water, that's carbonic acid. Okay? Now, the reason I say this is too restrictive of a term, if I were talking about this, I would say acidification. That would include not just carbonic acid, but sulfuric acid, hydrochloric acid, any other acids that are out there in the environment. They all eat away, weather chemically away at the material. It's not just carbonic acid. So that's why I say this is a little too restrictive. I say acidification. That includes carbonation and the others. Now, carbonation is probably the most common, okay? But you easily have the others. This carbonic acid easily dissolves limestone. If you think that's true, just think what sulfuric acid does to it, and nitric acid, and these others. They really easily dissolve limestone, and they're all out there as well. In fact, what is the air made up mostly of? The air in this room. What's that?
Nitrogen, oxygen.
Okay, what's the first you said?
Nitrogen.
Nitrogen. Close to 80% of the air in this room is nitrogen. Okay? Close to 20% is oxygen. And then the few percents that, when I say close to, the less than that, you got carbon dioxide, you got water vapor, you got all sorts of other things out there. Methanes, all sorts of things. Okay. When you see a lightning strike, what happens there, that's a physical thing. It's also sort of a chemical thing. But when it happens, some of that nitrogen that's all over in the air is forced, oxidized with the oxygen, and that forms nitrous oxide, nitrogen dioxide. There's all sorts of nitrogen oxides. And when they dissolve in water, you have nitric acid, which is even stronger than carbonic acid. So every time lightning hits, you get a little bit of acidification happening because of the lightning. Okay? So it's not all carbon dioxide. A lot of it is, but it's not. And any of those acids will easily dissolve in limestone. And that's what causes a lot of sinkholes. Places that are the limestone, there are actually some places that it's not really good limestone, it's actually called the chalk. Okay, and if that chalk is there, it really dissolves away. And just like all rain is slightly acidic because of those nitrogen oxides and carbon dioxide. You got all those things in it that form these weak acids, sometimes strong acids. They dissolve away those chalks and things. I think I mentioned the Grady ponds. When you see a field out there and then there's a real low area in the pond, I mean, under there was probably some chalk at one time, way deep, and when the rain water gets down there, eats it away, dissolves it, and the soil subsides. And that's what a lot of sinkholes are. So I would say most sinkholes come through carbonation or acidification, though some are physical also. Just running water underneath the road will take away the supporting soil, and the road gives way. And then the next, hydration. Guess what that means? What do you mean when you say, I'm trying to rehydrate?
Replenish with water.
Yeah, replenish with water. So hydration is reactions with water. Well, guess what? If you think about what I just said, when I said the oxidation is actually catalyzed, made to go because of the presence of water. So most of the time oxidation happens in the presence of water. It certainly does in your body. Carbonation is carbon dioxide dissolved in water, and these are other things reacting with water. Water, like I said before, one of the most active mineral chemicals we know about. It's one of the best solvents out there. Lots of things are dissolved in water. And why? Because of that hydrogen bonding. I mean, those hydrogens act like little acid eaters, and the oxygen acts like oxidizers, okay? They really react strongly with things, and including dissolving in water and combining with water, okay? Now, you mentioned mudslides early on. Where do you think when you say mudslides?
Where?
Huh?
You said where?
Yes. Anyone in particular?
California.
Second? California is infamous for its mudslides. And the reason for that, and the reason I mention it now, it says combining with water. Most of the clays around here are what they call one-to-one clays. I think we mentioned this before. A layer of silica, a layer of alumina, a layer of silica, a layer of alumina. Okay, those they hydrate a little bit. They all do a little bit. And you've probably seen the results of that when it's been really dry in the summertime. You look out at a clayey field, and what do you see? Cracks. Yeah, they look like little jigsaw puzzles or something. That's because the clays, when the water desiccates away, they shrink, okay? And when they wet again, they swell again. So that's combining with water. The one-to-one clays do it a little bit. Man, the 2-to-1 clays that are silica, alumina silica, silica, alumina silica, because these two silicas, they're light, they sort of don't like to connect to each other. They like to connect to the alumina above and below, but not to the silica in between, right? Well, when they get water, then the silica lets water get between the silica layers. What happens then? Those clays swell. And I think I mentioned to you before the bentonite that they use in building dams. When you have an earthen dam, they dig out the core of that and put pure bentonite in. They mine this out in Wyoming somewhere where it's really dry, bring it here through, and then when the water hits that, it swells up and fills and seals that dam, so there's not much leakage through there anymore. So that's combining with water. Now, why did I get off on that? Well, out in California, those are, we think of as newer soils. It's usually dry out there, and then the minerals that are out there decompose, they form these 2-to-1 clays. Montmorillonites, bentonites, and others like this. Well, then when they get it's usually a fairly dry climate. When they get a lot of rainfall, then those clays swell. And when they swell, they're slicker than they really will move easily. And what was a really solid structure here, now they just go down the hillside. That's what causes mudslides. A lot of the time are those 2-to-1 clays hydrating, combining with water, and then they lose their structure to hold themselves in place. Or things dissolving in water. And remember when we talked about our sedimentary rocks? They're formed by a process. Anyone remember what that's called? Again? Okay, that's called lithification. It's made up of two pieces, compaction and cementation. That cementation, that's what holds them in place. Water will sometimes dissolve the cementing agent, and then the particles fall apart again. So just like it's when they lose the water, they cement in place, and then when they reintroduce the water dissolves back again. So yeah, any reactions with water that are not mentioned above, this is hydration. Okay? Water is involved in just about every part of this. We'll learn later the transport is usually water too. Okay? Here are a couple of figures. In fact, both of these are in your book. This is figure 20.6, A and B parts. Now, just looking at this, I didn't know why they did it. I thought they were sort of showing that layering was horizontal. I said they did that in another chapter. What they're getting at here, every now and then you'll see, if you look carefully, places that the rock is really eaten away. That's because it was softer rock, more limestone or less strong, and the has actually dissolved that away, leaving some of these caves and holes and things in the rock because the water is dissolved by carbonation or acidification, and then hydration has transported it out. When you look at something like this, again, it's like the Yellowstone picture. Probably at one time, the whole surface was up here, way up here. And over time, the water is eroded the other way by hydration, carbonation, some oxidation perhaps, and then the water transports it away. So the water is constantly eating that. I hate to do this, but I'm going to. Here, again, at one time, this waterfall was out here, higher and further out here. And the water has been wearing away that highly resistant rock. Every time it goes over there, it's eating and dissolving and doing micro bits of that rock, but it is, because at one time the water went up to here, and up to here, and up to there, and the water has slowly eaten away. This is just highly resistant rock. Does that mean it won't dissolve? No, it just takes water longer to do it. And the more energy it has going over, the more likely it is to do it. So yeah, water is a pretty persistent thing. I don't know if you've seen an area, where water has dripped for a long period of time. You'll soon have a little well down there. Because water acidifies, it doesn't oxidize, but hydrates, dissolves things, and just wears it on down. That's what it's been doing there. Now, like I said, they mention biological, they don't anymore, okay? But biological weathering, as I've already mentioned, sometimes is physical, sometimes is chemical. Those little lichens, remember I mentioned on the rock? They have little bitty things like roots. I don't know if they call them roots, cilia or something. And they go down just like root hairs, make their way into the rock. They send out a little bit of acid, dissolve the rock, and use the minerals there. And they're breaking down the rock. So any biological process, usually it's chemical or physical, but that's actually done by a living plant. So let's look at soils. One of my favorite topics, okay? My master's and my PhD was in soils, okay? So I love this. They give it one slide. Thank you very much, okay? It's the only place they do. It's the most important thing on the planet, except for maybe water. These are mixtures. What a soil is a mixture of unconsolidated, weathered earth materials and humus. Okay? Now let's get that. Number one, it's mixtures. Most soils are not pure minerals of any nature. Okay? Mixtures of things. What do we mean by unconsolidated? They've been broken apart. Yeah, if it's consolidated, it's all still together. That would have been a rock. It's now unconsolidated. It's been split up, broken apart, weathered. Those three processes we talked about, physical, chemical, and biological, being weathered. Earth material, meaning at one time they were rock. Could have been igneous rock, could have been sedimentary rock, might even have been metamorphic rock. But those earth materials, but not just that, humus. Now, we haven't mentioned humus yet. This is the first time. Now, this isn't the stuff the Greeks eat with their pita. No, that's hummus, okay? Actually, human there. This is humus. What is it? It's altered, decay-resistant plant material. Now, it can be animal material as well, but most animal material is originally plant material anyway, right? Most of what we eat is plant material or animals that have eaten plant material, okay? So it all came from plant material. Now, what it means by altered, you can't tell it's plant material anymore. It's been changed enough you can't tell. Decay-resistant, that means it's not been oxidized away. Now, here in the southeast, we have this problem because we have high moisture content and high temperatures. And a lot of things will actually oxidize away. But in other areas of the globe and the country, the plant material hangs around a little bit longer. Ever been in a swampy area? Dig that soil up there, it was really blackish, okay? Sometimes it's sort of slimy, okay? That's really pretty close to being humus there. At one time it was plant material, leaves and sticks and things like this, but it's altered, but down to a point where it won't decay much further, okay? Now, if you're talking about soils, okay, and you look at some soil, and this soil is whitish looking, you say that's a sandy soil. And this soil is reddish looking, you say, well, that doesn't make it. You say it's a clayey soil. And this soil here, you see it's blackish looking. Which are you going to use for planting your plants? Oh yeah, because black soil is richer, right? Black soil could be that same sand, just with a black coating on it. It can be that red soil with a black coating in it. What that is the humus attached to the other earth materials. The more you have, the darker it looks, and as you say, oh, this is so much richer soil. In some sense, that a little bit is, but you see, most of the time the humus doesn't have that much nutrient value. It could have a little bit, especially if it came from cow manure or something like that. There is some nutrient value there, but most of the time, the reason it grows things better, it's better at retaining moisture. That sandy soil, the water just goes right through it. The clayey soil over here is hard for water to even penetrate. But you get humus mixed in with it. The humus will make the sandy soil hold water better, and it will allow the clayey soil to absorb water better. So humus is really a great water manager. That's what makes it rich. That's what makes it good. The dark color is not that rich in nutrient, though it may have a little bit. It's mostly the ability to hold and manage water. See, the sandy soil don't hang on to water at all. Sands are usually large particles, relatively large particle size, without any bonding exposed to the surface. The water runs right past it. The clays are tiny, tiny, tiny little particles, and they will get water all around them, but hang on to them for dear life. So the plant root comes down, the clay won't let go. The sand doesn't have any to begin with, all it's already passed through. What the humus does, it absorbs the water easily, but it releases the water easily. So plant root comes out, oh sure, yeah, I used to be a plant, I'll give you some water, It's not like that, but it's something similar to that. So that's why you want humus mixed with your soil. So if you're having issues of your soils getting too dry, either because they're too clayey or too sandy, mulch a lot. Okay. Number one, the mulch keeps the moisture there under the, but also when it decays, it adds that humus back to the soil. All right. The weathered materials could include your quartzy sands, which have almost no nutritional value whatsoever. Silica is not a good plant nutrient. So those are just there to keep the soil in place, basically. The clay minerals, now the one-to-one clays are not that rich either, but what clay minerals do, they have lots of sites, because they're such tiny little particles, lots of sites where they have exposed bonds, and they hold on to nutrients well. And water. Sometimes they hold on too well, but that's what they do. And your metal oxides, they tend not to hold nutrients well either. Your salts, some salts are beneficial, some salts are not. Like table salt, sodium chloride, you can't grow anything in that. That's why beaches don't have anything growing on them, okay? That's why the Great Salt Lake around there, nothing much grows right there because they're in the Dead Sea. That's why it's dead, because it's too salty of a soil. Okay? But other salts, like potassium chloride, that's a salt. That's what. Have you ever heard farmers talk about putting some potash on my soil? Potash is potassium. Okay? It's a fertilizer element. Okay? So some salts are good, some are not as good. Okay? Now, let me say a little bit about the salting. Does anyone remember studying in history one of the earliest civilizations? What were some of the early civilizations? You remember?
Egyptians.
The Egyptians? Guess where the Egyptians lived? Egypt, that was a good guess. What's in Egypt?
Sand.
The what?
Sand.
Okay. What goes through that sand? Now, that's why the civilization grew there. You had this fantastic river that was always bringing down moisture and mineral content, and that's what made nice fertile soils. Okay? Another early civilization. It's excellent. The Fertile Crescent, the Tigris-Euphrates Valley, Mesopotamia, they call it. Okay? And again, two great rivers providing lots of moisture and lots of mineral content. Okay? Well, civilizations grew and people began to irrigate with that water so they could grow more food, so they could supply more people and have civilization forming. And everybody didn't have to be out there hunting and gathering. Okay? That's what made civilization. Well, guess what happens when you irrigate the same soil over and over again with that water that's coming down containing all those nutrients? Well, the plants use the nutrients they want to use, and the ones they don't want, they leave there. That water evaporates. Those things that are not useful to plants, they stay there. Those are sometimes your salts, the salts that aren't usable by the plant. That's exactly what happened. Because what's the Tigris-Euphrates Valley now?
Desert.
Pretty much desert. And in a fair amount, the Nile is not nearly as productive as it used to be because the soils have gotten salted. I'm going to make a guess here. I bet you most of the food that you eat, a huge percentage comes from where? I see a bag of almonds there. Where did that come from? Do you know?
It's Phoenix, Arizona.
Phoenix, Arizona. Lots of good lush farmland out there, isn't there? If there's farmland out there, it's irrigated. What I was getting at, what's the biggest agricultural state in the Union?
California.
California, and how is that done? Irrigation.
They actually do farm almonds out there. They farm almonds
Almonds, where?
in California.
Oh yes, absolutely. That's why I thought that would say in California.
And I think I've also heard that's the reason why they have the drought out there, because they use it so much to farm the almonds.
Yes, they do. One of the huge problems out in California, and in fact, all over the world, and this is going to be more and more common, a lot of our problems are going to be water problems. If you think about right now, the southeastern U.S. is probably one of the wettest areas in the country. There's others a little bit. We usually get plenty of rainfall. I mean, not always, but we get more than most of everybody else. And yet, the states of Alabama, Florida, and Georgia have been almost at each other's throats for decades now over water rights. Okay? And if you think it's a little bad here, California, oh man, way more people have moved to California than California can support. They don't have enough water for that. So water is getting to be a very precious quantity, and yet, because of that huge agricultural business out there, and it's huge, they grow most of our lettuces, most of our almonds, most of our fruits, vegetables. In fact, the old joke say, were you from California? You seem to know a lot about it. Okay. We used to say, yes, California, the land of fruits and nuts. That was had political overtones. But they grow, the raisins, the grapes, the wines, just lots of things are grown in California, mostly with irrigation. And you know what we're doing? Salting up those soils. So who knows, unless we're really careful with our water management, that may turn into the Tigris-Euphrates Valley one day, not be able to grow much of anything. Now, there's still a lot of farming on the Tigris-Euphrates Valley, but they have to leach out a lot of those salts or somehow manage them. So anyway, more than I need to say about that. So, what are these soils? The book doesn't show it, and I'm not going into great detail, but they have what they call the soil triangle. It doesn't matter which one. put the sands up here, the silts over here, and the clays over here. And right near those corners are almost all sands, all clays, all silts. And as you move up the triangle, you're moving more toward clays, or the clays and the sands, so you get sandy clays, clay sands, and stuff like this. Here, silty sand, sandy silts, and things like this. Here, clay silts, silty clays, and things. But in the middle of that triangle, where you have a good combination of sand, silts, and clays, that's called a loam. Okay? A loam is a soil containing varying amounts of the sand, which are the coarse particles, the gritty particle that you can feel with your fingers, the silts, which are like flour. You can't feel much structure, but it's there. The clays are so small, you can't see them with a microscope, okay? And mixed with an abundance of your humus. Those are your loams, and they say that it's also known as topsoil. Really what topsoil is the top layer of the soil, no matter what it's made of. Sandy clays or clay sands or silts or whatever, that's your topsoil. The most productive topsoil is if it's a loam. So I don't really like, they say, also known as topsoil. Maybe out west that's what they call their topsoil and loams, but in most cases, the loam is just a good mixture of sand, silts, and clay. And here's why. Remember what I was talking about? The sands let water just flow through too fast. The clays are so packed together, water can hardly penetrate. The silts act sometimes more like clay, sometimes the other. If you have a good mix of those, then water finds ways to go through, but is retained at the same time. A loam does that very nicely. There's enough. Okay. Basically, what you're getting at is pore size. If I were to ask you, is a soil solid, liquid, or gas? What would you say? Okay. The correct answer is yes. Yeah. They are solid, but only about half of a good, healthy, productive soil is going to be solid. The other half is going to be pore spaces. Now, the pore spaces, to be a good, productive, healthy soil, would be half filled with water and half filled with air. So, yeah, the answer would be yes. A soil, a good, healthy, productive soil, is solid, liquid, and gas. You got to have gases, you got to have liquids, you got to have solids. Most of it we think of as solids, and about half of it is. This is rough, but of those pores, you want about half of it filled with water and half of it filled with air. If you have too much water, you call it waterlogged. Things don't grow well. Don't have enough water, it's dry. Things don't grow well. If it was all solid, nothing could get through anyway, okay? It would be a rock, and nothing would grow. So you want a good mix of those. Now, the topsoil is whatever's on the top, that top layer. Now here in the southeast, a lot of times our topsoils are measured in inches or even millimeters. They're really thin. Bad news. We overfarmed for a long time. Out in Nebraska, they measure the topsoil sometimes in feet because they just shave off buckets full of, talking about a bulldozer, bucketfuls of soil, move them over here, you still have plenty of topsoil everywhere. They measured it in feet. It was disgusting how good their soils were there. The subsoils are less fertile than the topsoil generally. They don't have the nutrient content, so in that way it's less fertile. They don't have the water holding capacity that the topsoil does, so they're less fertile. They contain more rocks and sometimes mineral accumulations, but that means rock mineral accumulation, and most of the time hardly any humus. It just doesn't make its way down. Now, what made the Midwestern soil so great is those prairie grasses. The prairie grasses, because it's sort of dry out there on the prairie, their root systems go way deep because the root system out there mining for water. And sometimes the surface doesn't have much, so they go deep. And the difference between grasses and trees, once the growing season's over with, the grass roots die. But if they're way deep in the soil, they're the humus that are down there way deep in the soil. So now you have good, thick topsoil. Okay? Whereas tree roots don't usually die in the winter. They keep living. Okay? They may not be doing much, but they're still living. But grass roots typically die. So that's why the Midwestern soils have such great, deep, thick topsoil. Of course, what did man decide to do, at least the white man, when we moved across there? Oh, look at this good, thick soil. Let's grow something. Let's dig. Oh, boy, this all this mats of grass here, we can't, let's dig this up. In fact, they had so few trees out there on the prairie that they actually built their houses with chunks of grass roots. Okay? They called it sod. The old soddings. They just made bricks out of the sod. They just cut them into maybe 1 foot square, and something like that, and use those as the bricks, and just pile them on, and they lived inside of them. I had a friend of mine who invited me out to their ranch in Sand Hills, they called it. Her mom still lived in a soddy. You couldn't tell that because it had a facing on the outside. It had, plywood, sheetrock on the inside. It looked just like a house until you looked at the window wells. They were like that thick. The walls were literally that thick because that's how thick they built the sod. Because it was really cold in the wintertime, that sod was a great insulator. So they used great big chunks of sod and built the house that way. The windows, she could have rows of plants in her windows, that was just amazing. So, that's the subsoil, the soil that's underneath that doesn't, those are the characteristics. Okay, I'm afraid I've done all I can with soils. Let's talk about erosion now. All right, erosion, and they don't specifically say this, but what they say is erosion is the mass movement of soil. However, that mass movement occurs. Okay? Now, let me preempt this and say, from a soil scientist viewpoint, erosion is in two parts. As I said before, detachment and transport. A good, healthy soil is going to stay in place, okay, because it has what they call good soil structure. But, say a raindrop coming from way high, and some of these summer thunderstorms, they start off, the raindrops look like they're that big. I mean, they splat your window and almost scare you, if you're driving down and it's just started. Okay, those things, the more mass they have, falling from way up high, they come falling at a very high rate of speed, that hits the ground and sprays like this, breaking apart that soil particle there and breaking it into little pieces, and that's the detachment. And then the rain goes running, and there's your transport. Well, the mass movement, the movement of soil, that's erosion. Erosion, a lot of you would buy this, but erosion is caused directly by gravity. Not all erosion, but most erosion. Because guess where the water runs? Downhill. Okay? So, and even if the water's not running downhill, where do those mudslides go? Downhill. Gravity is pulling it downward. So most erosion is caused by gravity. Now, if that is happening slowly, we call that soil creep. Okay, not that it's creepy, but the soil movement always down the steep slope, but the slow movement down, you really don't notice it happening, but it is over time. Now, I can remember in some elementary school class, in some social science class, we read about, it seems like it was France or somewhere in Europe, that what they did, the farmers, it was on sort of really hilly areas. And what they would do every year, this is back when labor was cheap and mechanization hadn't occurred yet, what they would do, they would dig out the bottom row of the field and haul it back over the top and pour it out there, because the soils tended to move downhill. So every year they hit the soil and carry it back up the hillside, okay? And it would creep on back down again. Now, if it goes faster than that, any slow to rapid downhill movement we call a landslide. Now, that means any land. If it's specifically wet, muddy land, we call it a mudslide. If it's only rocks, we call it a rock slide. If it's snow, we call it an avalanche. But that's the landslide. Any slow to rapid movement downhill when you can see that happening. The creek, you usually don't see it. It happens so slowly. But those are two forms, and both of them caused by gravity. Now, I've never seen this, but evidently it happens out west where you have fairly new mountain-type areas. The soil is thin, mobile, and fairly steep. And you'll see trees that grow up straight, nice, beautiful trees. Other trees that have sort of this varying amount of bending. Of course, trees are always trying to go to the sun. So they're always trying to adjust and grow up. But if the soil is creeping down the hillside, it's trying to carry the trees with it, but the trees are trying to grow up. And you will obviously see some of that in the west. Now, I was in the Navy in California, and in the Bay Area, San Francisco Bay Area, and a few times I had to drive to Sacramento. And that interstate just went pretty much due west, and they had trees planted in the median in the middle of it. Every one of those trees was leaning, but that was mostly wind. If you've ever been to San Francisco, they call Chicago the Windy City. I've been there once, but it really wasn't that windy that day, but I'm sure it is most of the time. But San Francisco is one windy city. I mean, it seems like the wind's always blowing there. And that's why the West Coast has all these wind farms. They're making electricity with that wind. So that's renewable, okay? This is an example of soil creep, okay? I've sort of sometimes wondered if I walked around much in Double Oak Mountain State Park, which is really hilly, if I'd see trees that did kind of this. I've never done it, but I think if I ever do, I want to look and see if I note any of that. All right. Now, erosion can be caused by several things, and one of them is certainly running water. The most important of all the gravitational erosion processes comes from running water. And again, the running water detaches and definitely transports that mostly soil material, but other things as well. There are 3 stream transport mechanisms. So what they're saying here, here's a stream of water running down. You can think of the Yellowstone River back there. You can think of any kind of thing. 3 transport mechanisms. One thing the water does, and we said this before under hydration, it dissolves materials. Okay? Water is always actively dissolving stuff. And if that material is that cementation in your sedimentary rocks, it dissolves the cement, there goes the sediment. Okay? It goes back to being sediment rather than rock anymore. But water also moves things by suspension. Dissolving is actually a chemical. Well, it's not quite chemical, but it's more chemical. It's the water, remember that hydrogen bonding? That breaks in and breaks apart the bonding of the other material, like that cementation, and then dissolves the material in the water. Y'all are really healthy people. What's in your container? The water. Okay, see, y'all are healthy people, but if any of you had any iced tea, if you think of iced tea, you can look, and you can basically see through it. It's just its color, and a lot of things are like that. But other things like milk, you can't see through. Why is that? because milk has suspended fat particles and protein particles and things like this, and calcium particles. They're suspended in the milk. It's not clear. Well, suspended materials in water, that's when you look at the stream and it's muddy, it's got suspended particles in it. When it's nice and clear, I bet you it's got lots of dissolved particles in it. You just don't see it because this solution is more of a chemical process. Suspending is more of a physical process. But not just that. You also move things along, rolling, bouncing, and sliding along the stream bed. Okay? Go back to that waterfalls at Yellowstone. Guarantee you, the bottom of that waterfall, that water's coming down with such force, there are rocks being moved, there's sand being moved, there's other things, and it moves along the stream bed and bounces along, dislodging, detaching other materials like soils or other rocks, and then they get moving down. Maybe dissolving some, suspending some, and just carrying some more along. Now, if finally it slows down a little bit, then it will deposit stuff out. Like going around the bend, you'll see that the sands are over here, the clays are over here. That will, when the water finally slows down, things fall out. Now, the stream bed evolves over time, and boy, this author likes this concept. Okay? Let's take a look at that. What would you say is in that water? Second?
Dirt.
Okay, yes, that's suspended materials. That water is, you don't see through it very easily. It has clay suspended in it, probably some sand suspended in it. It's moving pretty fast, it looks like, so it probably is carrying quite a bit of stuff. I guarantee you the stuff dissolved in there too, you just can't see it because that's clear, okay? But it has a lot of suspended, okay? It may actually be moving some bouncing, rolling gravel and other things, carrying that along as well, okay? That's the beginning of erosion right there. So here's your stream bed development. Now, we'll see it here, we'll see it later. These things look very, very similar because they are. They're related. A youthful stream, that usually comes when the landmass has been recently uplifted. Now, again, you have to think in geological time. This could have been over several thousands of years. It's slowly been uplifted. That's recent. Millions of years it's been there a while. Okay, so the landmass is recently uplifted, and when water goes through, the stream is going through, you have a very steep gradient. In other words, the waterfalls is a very steep gradient, but other, like this right here, you see it's higher here, lower here. That's a steep gradient because it's a fairly recent landform. Okay, landmass is fairly flat. But when it does dig out, it digs it out, hits that weak soil, rock or whatever, you have V-shaped valleys. Okay? You saw that in the Yellowstone picture. So the sides went down in a pretty sharp V. With no floodplains. There's no area where it just sort of slows down and hangs around for a while. Okay? You'll see boulders, rapids, waterfalls. That's all in your youthful stream development. Now, when it gets a little older, just like, well, y'all don't know, y'all are still youthful. You get a little older, you slow down a little bit, Don't quite do as much moving. The stream gradient now is less. It's smoothed a little bit. It's not so much like this, it's more like this. And it lowers, and the streams sort of tend to meander. They may find new routes to go. And sometimes those old people who just sort of wander around, don't really have much direction yet. Okay? So that's the maturity. Okay? Mature stream beds. In the old age, really slows down. Very low gradient, broad, gently sloping valleys. You've washed out for many years. Sluggish flow, I can relate to that. And you tend to have more flooding because there's not much gradient. So when you get a large input of water, it just rises everywhere. So you get more flooding. Now, if you have a pretty good map of Louisiana, Mississippi, Texas, or a lot of those lower states along the Mississippi, take a look at those sometime. The Mississippi River, wherever it starts up there, it's probably coming down pretty fast and great gradient, but at some point it tends to slow. And if you look at the Mississippi sometime, that's one long river. It doesn't go very far. It does this kind of motion all over the place. It's meandering like crazy, okay? But you'll also see along the banks of the Mississippi, you will see these arc lakes. And what they were, that used to be where the Mississippi or some stream was, and then it changed direction, but then this got separated, and it's now a lake. My wife's brother and his wife built a house, what they call it. It's not really a lake house, more of well, it's on a lake. The name of the lake is the Cane River Lake, I think is what it's called, or something like that. It's a big curved where the Cane River used to flow, and it changed its path, and then this lake was left here in the old riverbed, and they're on that, and there's no river traffic because it's not connected to the river anymore, but it's called Cane River Lake, big bend of a lake, okay, and that's when it's begun to meander. This is, Louisiana. It's a sort of flat, more of a well-developed, mature to old age area. Here is a graphic of that in a fairly recent landmass, okay, such as the Rocky Mountains. If you've ever been out west, those mountains go up very sharp. They're still growing, by the way. The Rockies, because of the plate tectonics, there's still growth there. And notice there, most of the valleys are V-shaped, okay? You have a lot of downfall, you have steep gradients. The rivers are fast and furious, usually not too wide, but they go really quickly, okay? You will see, they don't show any here, waterfalls in certain areas, okay? In the mature type time, everything's slowed down. The mountains have sort of worn themselves down. This is almost the Appalachians here. Most of the Appalachians are very rounded mountains. It's still got some gradient. There's waterfalls in the Appalachians. There's some beautiful waterfalls there. But most of the mountain tops are rounded and that type of thing. You get on further down here and there's even more of that. But then you get down to the old age, just about all the erosion has occurred. Everything's flattened out. Here's the place that used to be the riverbed, but then it changed and moved over here. You have a little bow lake is what we call it. I call it arc lakes. It's an arc island, but bow lakes. These bow lakes are fairly common. And everything moves pretty slowly there. Have a big rainfall upstream. This doesn't handle rapid movement of water, so all this area will flood. Okay, and that's why we say it'll flood. You have hardly any floodplain here. Everything's steep, it runs along. Okay? Those are your stream development. In half a dozen or a dozen slides, we'll see landform development, and they go through the same type phraseology. They use the same terms for it. And here again is good old think these are the upper falls. And I skipped over, let me back off just a minute. I don't really focus too much on these examples. Do we need to take a break? We've been at it for about, an hour and 45 minutes? Hour and 40 minutes? It would be a bad time if you want to. Okay, let's take a quick break. I'll pick up and do those examples then. All right. Like I was saying before, I sort of got to talking and not turning pages. Wanted to mention a few things that I did sort of skip over. One was a concepts applied on page 510. These are usually fairly interesting to read. This isn't very big, but it said, prepare a display of photographs that show weathering and erosion processes at work in a city environment. And I don't know exactly what they mean by that, but what comes to my mind is when they're doing excavation or building and stuff like this and expose a lot of soil, and then you suddenly get heavy rainfall and stuff. Not good. You can lose a lot of pretty good soil and do a lot of problems that way. Now, one thing that sort of amazed me, I don't know why Bessemer seems to be so flat. I mean, Birmingham, well, downtown Birmingham is fairly flat, but Bessemer, you go down the Bessemer Superhighway here, and if you have a rainstorm, there's water standing everywhere. There's just not a lot of runoff, and I guess that's because, here's another one of these. I got one earlier. But, so it seems like Bessemer is sort of controlling its erosion pretty well. Example 20.1, what is a slope and percentage grade for a mountain road that drops from 2 kilometers in elevation to 1.2 kilometers over a distance of 3 kilometers? Well, there's nothing we've done that said anything like that, but this is a pretty simple math concept. Remember what grade is? Rise over run. So what's your rise here? Or actually they call it a fall. 0.8 kilometers from 2 to 1.2. So it dropped 0.8 kilometers over a distance of 3 kilometers. So it's 0.8 over 3. So and then if you do that as a decimal, the 0.8 over 3 would be 27.27. And see, there's absolutely nothing in the text that shows these formulas. And I don't even know where they get some of that. I don't know where the 45% came from. I do not know. And they call that a 6% grade. That's sort of a mystery. What is the gradient of a stream in meters per kilometer that drops, drops 8 meters over a distance of 2.4 kilometers. Well, what is the drop? 8 divided by 2.4, and if you do that division, you'll get something on the neighborhood of 3.3 meters per kilometer. So those are, they sort of throw in examples like this, give you no background to them, so I really don't usually pay too much attention to them. But there was, some of them are pretty interesting, like 20.3. In 2010, a class examined a graveyard to measure the displacement of tombstones by the process of soil creep. Okay? By measuring the tilt angle on various tombstones, they determined the displacement to be shown on this table. The date on the tombstone, if it was a 1925, it had a displacement of about 45 millimeters, 31, 46 millimeters, 48, 30 millimeters, 65, 27, 70 was 20. What's the average rate of creep? You know, and you can read through that and see how they do it. Again, sort of a made up, I guess those are real data. The class did do that, but then they talk about creeping trees They showed the diagram of it, but investigate how the creep of soil has changed trees on the steep hillside. That's why I said I'd be interested to see that in some place like Oak Mountain State Park, just to see. Okay. There's another couple of examples here. I'll let you read through those, any that you think are interesting or valuable. Here's a picture in your text. This is, again, like I said before, in your book it's here on the slide set at both places, at the very beginning of the chapter and here. This is, I think, the Upper Falls, Yellowstone Falls. And by the way, you're a long way from it here. Look back and see it. There's an overhang here that you take these pictures from. It's a really nice area. And you can still hear the roar, even though you're probably close to a mile, if not more than a mile from it. You still hear the roar. It's just really amazing. And it keeps going. But this is a youthful landform. Steep valleys, rapid gradient. This water is rushing down here, and that's what keeps it eating away at the soil because it's moving so fast. The faster it moves, and I don't know if y'all are familiar with energy. The one form of energy is kinetic energy, which is 1/2 mv squared. 1/2 the mass times the velocity squared. So the faster it's moving, way more energy is there, and if lots of water is moving, big mass is there. So in every way, this is doing a lot of work on that stream bed at the bottom. Okay. Beautiful area. Please, sometime during your lifetime, if you can possibly do so, take a trip to Yellowstone. It's worth it. My wife has meetings, professional meetings, in Park City, Utah, right at the end of this term. In fact, the very 1st of August. And so it's right the end of our summer before our fall begins, so I get to go with her this time, and so we're going, and then we're going to drive over to Yellowstone, well, the Tetons, and then go to Yellowstone one day and eat at the Yellowstone Inn, your Old Faithful. And you were telling me about magma coming up in some of the geysers, or somebody said, oh, you were telling me that, yeah. Amazing. I'm going to see if I can read it or find out anything about that while we're out there. But this will be my 3rd time to Yellowstone, and every time is a treat. You see buffalo, huh? Fort Payne? No, huh?
Little River Canyon.
Yeah, you said Fort Payne?
Yeah.
I've heard about that. It sounds like a phenomenal place.
It's nice.
Yeah. I did go to some type of retreat or meeting or something up near it. I don't think we were quite in that, but that is a nice area up there. I want to.
I didn't go to the bottom. I was like up on one of the. I just drove the scene, right? Along where you can look out. And it was really nice.
Yeah.
It's kind of hard to get down because the road is not very good. But you can go down to the bottom and there's like park and camping and stuff. Because it's a lot more work.
So it is a national park. Yeah, that's beautiful.
Yeah. And I mean, Smoky Mountains National Park is another great place to go. But for geological reasons, nothing in the world is like Yellowstone. I mean, you just got so much stuff there. But yeah, we got a lot of pretty stuff around here too. All right. I mean, I've never been to Yellowstone when we didn't see buffalo and we didn't see bears and we didn't see the sheep. I mean, there's wildlife too. It's just amazing. It's pretty nifty. The example on 20.7 is another one that They just throw it in there, and I'm not really sure why they did that. Okay, so that stream development, I wanted to mention that again. And whatever was to go there was obviously didn't make it. Along, one of the last things we mentioned here was the no floodplain in the youthful, meanders over the floodplain and mature, and you get a lot of flooding in the old age. So they're talking a lot there about floodplains. That's on page 513, where they talk about this, and you can follow it there. And then toward the end, and especially when you're getting to this old age, very low gradient, broad, gently sloping valleys, you're basically almost talking about a delta. Okay? So that's the next thing we're going to hit here, are deltas. Okay? Now, this isn't a sorority or anything, but okay. What this is deposits of sediments at the mouth of a river or a stream. Because what has that moving water been doing? Picking up stuff and hauling it downstream. Gravity, again, that's gravity fed. What pulls water downstream, pulls soil downstream, pulls all that stuff, and it pulls it down, and when it's moving rapidly, it carries a lot. When it starts slowing down, some of it starts falling out. And when it gets toward the end, right where it's about to go into the Gulf, ocean, or lake, or something like that, it really slows down. And when it does, the sediment starts falling out. All that stuff it picked up there, the stuff it carried along, the suspended stuff, it starts falling out. And as it does, you start building new soil at the bottom. The stream flow dissipates into the ocean or the lake or the Gulf or wherever, and the water just sort of goes there, the soil is left behind. The erosive and sediment carrying abilities are lost, so now it drops the sediments out. Okay? I can't guarantee this, but I would almost be willing to bet that probably a few hundred to 1,000 years earlier, that was the shore back there. All this land that you see here has been settled out over a course of hundreds of thousands of years. And more is still settling. Okay? As it shows here, here was the sort of the bedrock, the naturally occurring material, and then your river came down and started depositing stuff, slowing down and stuff, and then the slower it gets, the more it deposits further back, and this is that floodplain type area, and you're over years, decades, century, millennia, you just keep building this. Now, again, I can't guarantee this, but I would almost be willing to bet this is a very good thing, but there is Louisiana. That's where the Mississippi ducks into the Gulf. See how it bulges out there? My guess, all that is sedimentation. It's all a big delta. And I bet you originally that went almost flat across here. All that has been deposited over time, over lots and lots of time. Where is it getting it from? Everywhere here. The Mississippi, well, if we get far enough along, the Mississippi starts up here in Minnesota, goes down here, but it's joined by the Missouri, which starts over here and goes down. It's joined by the Ohio that comes here, the Tennessee, all these feed into it. Basically, the vast majority, probably more than a third of the continental U.S. drains into the Gulf of Mexico and Mississippi. That's a lot of sediment that has been washed off, eroded away. It winds up in the rivers carry it on down, drops it off at the Gulf of Mexico. So I bet you the state of Louisiana is probably several percent bigger than it would have originally been because it's still forming new, and these are called deltas. area where that soil has been dropped off once the river slows down. And whatever it gathered up there is dropping off down there. Now, next is glaciers, okay? Why are we talking about glaciers in a chapter on forming the, shaping the Earth's surface? Glaciers are what? Masses of ice on land. Do they move? Yes. They're just very, very, very slow moving water. The reason it is, it's solid water. And guess what? It still goes downhill. But at a very, very slow rate of movement. They form from the snow that has been accumulated over a number of years, anywhere from 5 years to 3,500 years. There are glaciers in existence that have snow that's that old at the bottom, okay, of those glaciers, okay? Two major classifications of glaciers. One is called the alpine glaciers. Now, it has another name, valley glaciers. Where do you reckon they get the name alpine? Think of a mountain range in Europe. The Alps, exactly. They were probably named alpine glaciers because the people who first named them were Europeans, okay? And there being mountain range over there, the Alps, and those glaciers that were in the Alps were called alpine glaciers. But they are still called that whether they're in China or Timbuktu, you know. They are called alpine glaciers. They form at very high elevations. And at very high elevations, remember, the air is thinner. There is more heat is reflected back to the sun more easily because you have less atmosphere there to surround it. So it's very cold up there. And most of your precipitation, basically all year long, is snowfall. Okay? So all that snow falls. It doesn't melt. It doesn't evaporate too much. So it just piles up. Okay? So the snow forms at high elevations and fills the valleys, and then the weight of the snow moves it slowly downhill. And that forms a better name for it would be valley glaciers, which they always call them alpine glaciers. The other kind of glaciers are your continental glaciers. Okay? These cover large areas of continent. Today they're predominantly in Greenland and Antarctica. However, Canada does have what they call the Columbia ice fields. Big continental glacier. It's not as big as it used to be. Okay, it's up in, I believe it's in northern British Columbia. We went up there on one of the trips we took with Karen's family. My wife's family used to do a big trip about once every 3 or 4 summers. You know, they plan it and save for it and stuff like this, and we go. And we went up to Canada and just had a great time up there and went up to the Columbia ice fields. The trouble is, I'm sure it doesn't show on here, but it was somewhere over in this area here. There's Alberta, Canada, this is British Columbia. It was somewhere up in this area, I think. Okay? And someone, when they first discovered, I mean, they've been there as long as the planet has been, probably since the last ice ages or something. But when we started recording things, someone put a stake or drove something down where the, what they call the tongue of the glacier finally ends and it's melting, you know, and going out there. To go from where that was, and that was in the early 1900s, to go from where it is now, where the tongue of the glacier is, have to walk more than a mile over just a little over a century. It's retreated that far. Is there no global warming? I don't know. I don't want to get into that, but good. But in Greenland, they're pretty much retreating too. Antarctica, sometimes I hear they're retreating, sometimes I hear they're holding fast pretty well. However, it seems like I heard recently a huge chunk of ice fell off of Antarctica and went into the sea. And I thought someone said it was fairly close to the size of the state of Rhode Island. That's hard to believe, but it seems like we're losing them. In Montana, there's a Glacier National Park. Beautiful park up there. My wife and I went there once. It was named that because I don't know how many glaciers it had back then. It was in the teens or 20s. I think there may be 6 left, and they're getting smaller. Okay. Ernest Hemingway, back in the probably 1930s and 40s maybe, wrote a novel or short story. The title was The Snows of Kilimanjaro. That's in Africa. It's one of the tallest mountains above the surrounding area. It's right on the equator, but it was so tall it had a glacier. Okay? And here is Kenya and Tanzania. Mount Kilimanjaro is right there. Okay? Very, very tall, probably the tallest peak in African continent. And it used to have glaciers. And that was the snows of Kilimanjaro. If you were to go to Tanzania today, you see a big mountain. I don't think you'll see a glacier. I think it's completely melted. Okay? So that's another thing. But glaciers are big masses of ice on land that move because of gravity. Here's a picture of what kind of glacier you reckon that is. Alpine or valley glacier. So it's actually starting somewhere up there, making its way here. It looks just like a stream or a river. It is. It's just frozen. But not frozen completely in place because you can't see it, but it is moving ever so slowly downhill. In fact, probably at one time, these mountains almost were completely across there. It has found the path of least resistance and followed that and eaten its way down. Okay? That's the Valley Glacier. How deep it is, hard to say, but the deepest part could be hundreds of years old of ice. Okay. Do glaciers erode? Sure they do. It's just a very slow erosion, but they do erode. There's 3 mechanisms. This book loves 3s, don't they? Okay? The first of these is called bulldozing. Okay? That's at the front of a glacier where that ice there and all that weight behind it is pushing down. Well, that ice is, anything in its path basically gets moved out of its way. Sort of like a bulldozer. Now, I believe it was the Canada trip. We went to an incredibly beautiful lake way up in the sticks somewhere. And the name of the lake was the Moraine Lake. And why it was named that, because it had been a glacier back in probably the last ice age, and it had bulldozed its way through and was picking up rocks and stuff, pushing them ahead, but then finally the weather changed and it had less pressure, and over time melted. Well, this big pile of rock that was bulldozed up in front just sat there. And that became a dam, and the lake filled behind it. That dam is called, the deposit is called the moraine. So therefore, behind the moraine was Moraine Lake. Some water makes it through, okay? It would have to, but it really held it in place pretty well. I mean, literally, it looked like someone took chunks of mountain and just threw them down there, because it literally was bulldozing these, huge boulders, the size of houses and things like this. Just, all sorts of angles and stuff. They weren't natural. That's where the Okay, so that's one way that glaciers erode. Out front, they bulldoze. Now, underneath the glacier, underneath the hundreds of feet of ice, think of all that weight that would be. And this is slowly moving downhill. Well, that underneath part, that's really hard ice. But that ice may, under pressure, sometimes melts a little, but then refreezes. And if it refreezes, well, just the weight of that crawling across a landform, that produces a powdery, silt-sized rock flour. I already said that silt was like flour, so this is almost redundant here. Silt-sized rock flour. That one time was rock, okay? The glacier ground it down. It's just like grinding corn at a grist mill, you know. It just ground it and ground it and ground it. And that's abrasion, okay? And then, this is what I was talking about. These two are fairly similar. The glacier, the water will sometimes melt a little bit and then refreeze, and it may refreeze around the rock, okay? Well, now it's sort of like that glacier has a tooth in it, you know, and as it goes down, that glacier water freezes around surrounding rock, pulls it along, and that's sort of like a bottom pile, you know. It's grinding up or plucking the rocks as it freezes, and then that uses it to abrade more. Now, I've mentioned a couple times already today the ice ages, okay? Now, I don't know all the mechanisms for it, but one of the ice ages must have come down, and that glacier, and this was continental glacier covering large land areas, must have come down and was digging into the soils here and maybe pushed up things right along here, and then when they started retreating and melting, they think that's why the Great Lakes were formed there. Now, I don't know if that's still the current problem, but I'm wondering if Hudson Bay may have been made the same way. It may have been softer material there, and the glacier just was dragging along, pushing things ahead of it, and then when it retreated, formed glacier. I don't know. I'm just guessing. But I do know this. Remember I mentioned how much great topsoil we have here in the Midwest? Where did that come from? Thank you, Canada. The glaciers came across Canada, grinding, bulldozing, abrasing, plucking, carrying along, and some of those ice ages were 4 really big ones, and they made it down into Nebraska and those kind of areas of the U.S. That's where they stopped, and then melted and started dropping off all that soil they had picked up. Really good soil. Topsoil from Canada put on top of our topsoil, and we have some of the best farmland in the world right there. Thank you, Canada, for sending us your topsoil. Okay, inadvertently. You didn't mean to, I'm sure. Okay, but those are 3 forms of glacier erosion. Happens really, really, really slowly, but it does happen. Okay, and you'll see this sometimes. What was originally in a fairly youthful landform, these steep V-shaped valleys and stuff, rounded peaks and stuff. So this is rounded, would be a little bit older than youthful, but not quite mature yet. Then if an ice age comes or a glacier fills the valley rather than the river, and it just snows and gets deeper and deeper and deeper, and then the glaciers are what's moving incredibly slowly, but still moving down those things. And then if they finally stop and start retreating, what's left? Rather than V-shaped valleys, you have U-shaped valleys. That is a definite sign. One time there was a glacier made its way through here. Everything else looks like it could be. And they have these, what they call hanging valleys. This glacier fed into this one, but this one cut deeper, so you have a hanging valley there. You have this U-shape, and then it's a very abrupt drop-off here, you know. That's because of that. also what was sort of rounded peaks here, the glaciers ate away until now they're sharp again, like they were probably when they were first formed. Okay? You can see right here was probably a glacier ate its way down. Now it's just sort of a thing. So some of these sharp peaks here are called horns, the top part. The ridge there was called an arete. Some of these areas here where the glacier sort of started there is called a cirque, or a cirque, I think that's how you pronounce it. There would be another one, maybe a little one there. And then you might have a tiered area here. These would be rock basin lakes. Maybe they came down and pushed rocks in front of them, but then get cold again and start growing again, but not come as far as it did the last time. And actually in Alberta, Canada, I think it was, we went up. We were driven by food, not by our adventure, but by food. We had heard there was some of the best chocolate cake at one of these stations up in one of these, near one of these lakes. So we made, I mean, an hour to hour and a half, or maybe even longer, hike through the mountains, going up almost all the time. And we saw some really pretty smaller lakes on the way. Finally got to the top, and they had some really good coffee cake. And we said, "Oh, you don't have any more chocolate cake?" "Oh, that's the next one. That's another 8 miles up. We'll sell it for coffee cake." Okay. The chocolate cake sounded good, but it didn't sound that good. Okay. So anyway, we were going through a series of it. It wasn't as stark as this. It was deep, rich forest the whole way. But you go up and suddenly there'd be another way. Okay. All right. So water causes, that's a major form of your erosion. Ice, which is a type of water, frozen water, that will do erosion, but it's a very slow erosion. There is one other, okay? And by the way, there are some pretty pictures in the book. I see a valley glacier on Mount Logan in the Yukon Territory. That's in very northern western Canada. It borders on Alaska up there. They call that a valley glacier. It sure is a broad valley, okay? There's a picture we just looked at. This guy likes these mistakes and misunderstandings. This one's a little on the weak side, but he's using an old phrase. "Oh, that's as unchanging as the hills." He's saying, hey, guess what, folks? The hills are always changing, okay? And they really are. It's just a very slow change. And that may be what they were talking about. If we're changing, we sure are slow about it, whatever. Okay. But there is another form of erosion, and this is wind erosion. Anyone think of a major thing in the U.S. history where this occurred? Any of you ever see Oklahoma or read Grapes of Wrath? The Dust Bowl, exactly. Wind can definitely do some erosion. Considerably less efficient than water or ice. Water and ice have a fair amount of mass to them, weight to them. That contributes to the detachment and transport, but wind can definitely erode as well. Two major processes here, and this is almost the same as what we talked about before. Abrasion, we talked about that with glaciers. I talked about it some with water erosion. I call that the detachment. That's the abrasion that wind is doing what they call natural sandblasting. Now these things is sort of a circular process, kind of like the rock cycle. The wind blows along and picks up sand particles, okay? The sand particles hit a rock. A lot of energy in it. They break other particles off, like a sandblaster. That's what they say. That's abrasion. It produces these ventifacts. In other words, those are wind-created features, okay? Some of these that you see, especially out west where it's not had that much water erosion, you'll see some of the wind erosion. They've made some really amazing shapes and things. The shape can depend on the prevailing winds. And I said earlier, I think I did earlier, we have prevailing winds mostly from our west because we're in the temperate region. Most of the winds are coming from the west. But then you'll get some shifting and stuff. So you'll see different shapes to the west side of something than you'll see on the east side. Then the second, that's the abrasion, which is sort of the detachment. The deflation is when the loose material is picked up, carried away by the wind. That was a dust storm, the dust bowl. The wind picked it up and carried it away. The wind first abrased it and knocked it loose, and then the wind picked it up. That's abrasion, deflation. Now, the wind-blown deposits. If you've ever been to the beach, you know just in from the beach you usually have the sand dunes. Okay? Those have mostly been, some water has forced the sand up this way, but the wind basically shapes those things. The dunes are low mounds or ridges of sand or other sediment that basically have been blown in. Here is an interesting term. Strange spelling. It's pronounced lus. Wasn't there a company that made, I think mostly women type products, really nice stuff, smelled good and all that kind of stuff. It was called Lus, L-U-S-S. It's pronounced the same way as that. I think it's out west or Canada or somewhere, but somewhere we've been, we saw that. I never see any stores like it around here. What Lus is fine dust that's deposited over a large area. Now, Brian mentioned the Dust Bowl. A little bit of history there, okay? Our continent was so blessed with this great grand prairie. Basically goes from states like perhaps Ohio, Indiana, all the way west to, say, Colorado. I mean, just a huge area from north to south, from Canada down to Texas. That's the prairie. And that prairie grew really great grasses, okay? And the grass is what held the soil in place. Like I said, it was sort of a dry environment, so those roots from the grasses went way down, okay? And that's where the buffalo roam. And that's why we could support hundreds of thousands, huge herds of buffalo. There's enough water there and plenty of grass for them to eat. It must have been an incredible experience for those early settlers to go across that country. Hard, miserably hard, but what they could see there was just absolutely incredible. So here came the settlers. The white settlers going across, and they said, look at this good grass growing here on this fantastic soil. Man, let's chop this stuff up, plow it under it, plant us some corn, plant us some wheat, I don't know if I had soybeans right now. We could cultivate and really make a killing here. So we broke that sod, that incredibly dense, thick, well-structured sod, out, sometimes just chunking it, getting it out of the way so we could get to the soil that didn't have all those roots in it and plant it. And it just happened to be the seasons when we got there were having decent rainfalls. Unusually great rainfalls, but we didn't know that. We thought it was always that way. So we raised some great corn and corn husker steak, just fantastic crops. But then the normal weather pattern came in, which was a lot drier. We had gone away with all that good sod that was on top, and now all the winds came. The winds come whipping down the plain. No problem. And those winds picked up that unprotected soil and hauled it out, dried out, and hauled it, and you had the dust bowls. And literally, they would find, I think I read somewhere, maybe in this book, in Philadelphia, deposits of lus that had blown all across the country, from Kansas to Pennsylvania. That was, we just don't know what we're doing sometimes. remember how I mentioned that the rivers tend to just meander about, especially when they get in the low-lying area? The Nile does that too. And that meandering, then periodically, usually once a season, they'd have these floods that would come. All that low-lying soil would just get flooded. And they said, you know, this is just messing up our agriculture. Let's dig us some channels straight in the river, you know, dig us like the Tennessee Tombigbee or something like that, so we can be more efficient with things. And let's build a dam, the Aswan Dam, way up on the Nile. You know, good fall down there. Produce a lot of electricity. We don't have much oil, let's produce hydroelectricity. Well, the combination of doing those two things, they cut down on the floods for sure, but guess what they also did? They cut down on the soil deposits coming downriver, and suddenly the crops were not as good because they weren't being replenished by good, fresh soil. That was a result of the flooding, but it deposited really good soil. So now the farming is not nearly as good. Egypt cannot feed itself anymore. Weren't we smart? Clever, okay? Sorry. Okay, this shows the ventifax, okay? The prevailing westerly winds come in here, pick up soil particles, sandblast that side of the rock, loosen the soil, blow it away, okay? So you get these ventifax, smooth, rounded area here, sort of abrupt on this side. Now they say if you have a persistent shift in wind direction, you can actually cut some coming back. But what they're getting at is no matter what's going on, that polar rock can't stand up against water and rain and everything else. It's going to slowly be weathered away, physically, chemically, and perhaps even biologically. All right, then they get to the formation of the development of landscapes, okay? But before we do that, on page, so close, no cigars, acid rain, okay? And they talk as if carbonic acid is the only one doing it. It certainly contributes big time. But I suggest to you where you have pollution and a lot of sulfur in the air, as in your factories and wherever you burn coal and gasoline, diesel and stuff like this, you get sulfur dioxide in the air. Mix that with water and you got sulfuric acid, much stronger than the carbonic acid, so you don't need as much of it. And then every time you have a lightning strike, you get some nitrous oxides form. They combine with water and form a very mild nitric acid or other acids like this. So notice the table here. Hydrochloric acid is almost 0 pH. The lower the pH, the more acid it is. Your stomach acid is one of the next none. Believe it or not, you have some really serious acid down there. If you've ever had some real bad acid reflux, that's why it eats away your esophagus so badly. Your stomach lining is designed to contain the acid. Your esophagus is not. So that's why, you know, if you've been nauseous and throw up and it's that really stinging, burning stuff, that's that stomach acid. It is strong stuff. That's what does your digestion for you. Thought I had them, but I don't know. Okay. Lemon juice, you think that's really dangerous to your teeth? Stomach acid is more acid, but lemon juice is really acid, 2.2 to 2.4. Stomach acid, 1.86 to 1.8. Vinegar, 2.4 to 3.4. Carbonated soft drinks, look at that. Did you know you were drinking that much acid? Okay. 2 to 4. Whoa. Grapefruit, wow, I know that's acid. I didn't know carbonated soft drinks were more acid than that was. That's 3 to 3.2. Oranges, 3.2 to 3.6. Acid rain, more acid than tomatoes are. Okay? 4.0 to 5.5. Tomatoes, 4.2 to 4.4. Potatoes, surprisingly, are somewhat acid, 5.7 to 5.8. Natural rainwater, no pollution contributing, is still 5.6 to 6.2. So it's slightly acid. All rainwater is slightly acid because of the nitrous oxides and things that naturally occur. Milk is 6.3 to 6.7. Pure water, absolutely pure, distilled, deionized water, 7.0. And then you get on the alkaline side and you can go on up, from there. A very good little blurb to read. Okay? There's another blurb on concepts applied to dune angles. If you are down at the beach or somewhere and want to do that, I'm sure that's what you do at the beach. You could measure those. People behind the science, John Wesley Powell, a really congenial-looking old guy, isn't he? Okay. You can read that. There may be some other people mentioned. I don't see many in here. Okay. So now we're ready for the development of landscapes. All right. First, a few definitions. What is a landform? Well, those are the Earth's surface features. For instance, Shades Mountain, Red Mountain, Double Oak Mountain. Those are the landforms, Earth's surface features. Okay. Stone Mountain, down in southwest Georgia, just across the Chattahoochee, is what they call the Fort Valley Plateau. There's a town in West Georgia called Fort Valley. There's a college there, or maybe it's a university now, I don't know which. But anyway, they're on Fort Valley Plateau. One of the best peanut growing areas in the world, okay? Just a great feature for raising peanuts. So these are the landforms, the Earth's surface features. Some of these broad features would be, like I mentioned, the mountains, the plains, the Great Plains would be a feature, broad feature. Plateaus like the Fort Valley Plateau or other plateaus. Then you have the minor features, like the hills, okay? Why is this hill here? What makes it? The valleys, okay? Yeah, that river cut through canyons. A lot of erosion occurred. Now, it's sort of hard to tell in the city, though, isn't it? I get sort of tickled. Remember when we went to Sanford? What was that road we were on? Lakeshore Drive. Did you see the lake when we were driving by? No, they evidently drained the lake, filled it in, and built a shopping center. What's that song? Paved paradise and put up a parking lot. Yeah. We've done some dumb things in town. But get out in the areas and you'll see some of the major features of the big things, the minor features of the smaller. What's some of the generalization? Well, part of that is based on rock structure. Why did the Yellowstone Falls happen where they did? The rock structure was weaker where that water came down, stronger on the sides. It's resisting the... Why is the waterfall there? Because up to there, it was weak structure, hit some granite or something there, it's having a hard time. Washed it out below, it's having a hard time eating its way down, but it's going to do it over time. Okay? So what is your basic rock structure that created these features? And it's not just all rock structure. This, again, the guys from Arizona, so they think more in terms of that. Sometimes some of the hills are because they're clayey. When we built our place over in Georgia, just a 2-bedroom bungalow, it's on a hill, and there's a sense of, well, why is this hill here? Why isn't it flat like some of the rest of the farm? You start digging there. When they went to dig out the crawl space for it, they said that guy almost beat himself to death. That big old bulldozer he was doing, he was having a terrible time making any progress at all. That clay was so thick, so heavy, so hard. It was really dry that time of year. He could not make a dent in it in the bulldozer. And literally, he broke his health trying. I mean, he was out there, and it was frustrating, and he was going to beat it no matter what. It beat him, okay? Other areas didn't have that clay. That's why that hill was there.
Never heard of dynamite.
Yeah, you probably considered it. Okay. So the generalizations are based on the rock structure and then the weathering and erosion, and basically those go hand in glove. The rock structure would resist the weathering. Places you didn't have that strong weathering, there where you had the weathering and erosion. So again, these are all. And then the stages of erosion, was it early on, long time, had people done things to resist it. There was a place over in Georgia, I don't know exactly where it was, I never saw it, but I heard my professor talk about it there. It's called the Little Grand Canyon. Okay? It was not natural. It was an area that was a fairly sandy area, but had pretty good things. But someone did something stupid. I don't remember what they did. They cut a road through it or something and loosened up the naturally resistant, and then when the rains came, there was nothing to keep it apart, and it just kept eating away, and there's a huge area that's completely non-habitable, non-farmable, and everything else, just because someone that had some pretty major stages of erosion that happened over a very short time. Now, the Grand Canyon in Arizona, that happened long before anybody was there, so that's a natural feature. So let's look at these three. First, the rock structure. This determines the shape of the minor landforms. I think Stone Mountain again. That's definitely a minor landform, not major. It refers to the type of rock. Usually your igneous rock is pretty hard, resistant, weather-resistant rock. Okay? The metamorphic rock can sometimes even be harder than the igneous rock because it was formed under more pressure and more heat. And quite often is resistant to chemical weather. Okay? Whereas igneous rock may be susceptible to chemical weather. Okay? But igneous is usually pretty hard, and metamorphic may be even harder. Sometimes, though, the metamorphic rock is more brittle. So therefore, say sandblasting and stuff like that may actually eat away at it worse than it would an igneous rock. So sometimes. Then your sedimentary rock, hey, guess what? That was formed from sediments that already broke it down before. It's just compaction and cementation. That cementation was left over by water. It can be dissolved by water. Okay? It's really susceptible, I would say, both to chemical and physical weather. So the sedimentary rock is usually your softest, most easily eroded rock. Now, some rocks does have this attitude. No, that's not what it means. The attitude of the rock means which way is it facing, what is the thing. It's the effect of disturbance by faulting or folding. Okay? How did it get there? What was the result of that? That's the attitude of the rock. The faulting or folding can hasten erosion. Because guess what? It was solid, now it isn't. Now you got a crevice, water can get down there, you can have the wedging by freezing, lots of things can happen and make pretty relatively rapid changes. Okay? Weathering and erosion processes, we mentioned these all chapter pretty much. Influenced and controlled by such factors as climate and elevation. Okay? Now when you, I'm good with that. Climate, we're going to talk about it here. Elevation, I don't think they're going to mention too much about that. So how would the weathering and erosion be affected by elevation? Well, again, the steeper it is, the more likely you are to have erosion. The harder it's going to be to keep that soil in place. So elevation and the change of elevation, I think, is important. But let's look at climate. There's two big features about climate that affect weathering and erosion: water and temperature. Guess what we've got abundance of? Both of them. Okay? So we're going to be, and we are, in the continental U.S., our soils are the most heavily weathered. The Appalachian Mountains are really highly weathered. Of course, they're really old too, but because we've got high temperatures and lots of rainfall. Remember, just about all the weathering processes, involve water in some form or another. The chemical weathering, every one of those. The erosion, every one, all that is highly affected by water. So the moisture's there. Temperature. This will, in fact, impact both biological and chemical. And the rule of thumb is about the same. Starting at 40 degrees Fahrenheit, that's just a little above freezing. For every 10 degrees you go up past 40 degrees, you double your chemical rate of activity. So you go from 40 to 50, you double the chemical activity. Go from 50 to 60, you double it again. 60 to 70, you double it again. 70 to 80, you double it again. 80 to 90, you double it again. Guess what? Outside now, prime conditions for lots of chemical activity going on, because we've got warm temperatures and moist climate. And what's more, our warm temperatures happen all year round. Up in the far north, northeast, Midwest, those areas, I mean, they'll be below freezing for days, weeks, some of them months on end. There's no chemical weathering going on there. Everything comes to a stop. If it's ice and covered with snow, there's no erosion going on. Everything sort of comes to a stop, okay? And then when it finally starts warming up again, everything picks up. Here, it never stops, okay? In January, you'll have 50-degree days, maybe even some 60-degree days. The rate of chemical and biological weathering keeps on trucking. Slows down from summer, but it keeps on trucking, okay? So the chemical weathering is dominant in these warm, moist climates. The landforms have softer, rounded outlines. Look at the mountains around here. There's no steep, sharp peaks. They're all rounded, okay? Whereas in the dry climate, the mechanical weathering dominates. Your wind, your abrasion, and those kinds of things will dominate. Sharper, more angular outlines are more common than in the dry climates that you have here in moist climates. So yeah, lots of things influence. The weathering and erosion processes certainly do influence. And then here comes the stage of development. Have we seen this before? Before we were talking about valleys. Now we're talking about landforms. Okay? The stage of development describes the cumulative effects of all those formative processes. Your youthful landforms, where the weathering and erosion effects are still at the early stages, it's happening. You have the valleys, that means there's erosions occurred, but it's not rounded. Okay? The mountains have steep peaks, narrow, steep valleys. That's early, youthful. Your mature landforms, original structure is worn down. Now the peaks become a little more rounded. The slopes are a little more gradual. The stuff that eroded off the top is filled in those deep valleys. So now everything is a little less abrupt than it used to be. And then finally, when you get in old age, everything, all your mountains have worn down, the valleys have filled in, everything's getting nearly flat or rolling plains. And one type is called the peneplains, the nearly flat surfaces that there's just no landform that's going there. Another is monadnocks, which I've never read or heard of anywhere but this book, and that's hills of very resistant rock. And I would also suggest perhaps resistant clays and things like that as well. So peneplains are the flat surfaces, the monadnocks would then be those southern hills there that you say, why are these here? Okay, and then you have rejuvenation. Goes through this, proceeds, but then land is uplifted again. The whole process starts over again. Is it rapid? No. Do you notice it? No. But it happens gradually and is always happening. Sort of like the rock cycle. Everything, what goes around comes around, is an old phrase. Okay? Boy, this guy I think really likes his glaciers. Here's another one. There was one really pretty picture of a glacier, or was that on the slide set? Maybe that was on the slide set. I thought it was here. But here is the a melting glacier, a source of stream that flows through the valley. That's a very youthful landform. Okay? Now there is some roundedness there to the hills in between there, but it's still fairly, those valleys are pretty steep. And I say it every time, and I'll say it again. Nothing replaces reading the chapter. And I would say more than once, too. Okay? Once you've read it, here's a summary, and again, I think last chapter and this one too, very short summary. It doesn't mean there's not a lot of good stuff in the book, but they just left a lot of it out of the summary. Very short list of key terms, okay? Maybe why we were able to finish the whole chapter today. Probably one of the shortest that I remember seeing. Applying the concepts, 45 questions, that's a bit on the short side too, but good questions with answers given. Questions for thought, about normal, around 18, and for further analysis, maybe one or two fewer than normal, about 3. More invitation to inquiry, the frost wedging, if you want to read more about that. And then if you really got excited about those examples we saw in the text, there's some parallel exercises you can look at. Group A have answers in the back, and Group B do not. Okay. Wow. That finishes the chapter. And somehow I think y'all are as relieved as I am, but maybe not, I don't know. What we can do right now, we've got another 40 minutes or so, right? Don't let me cheat you out of any time. We could go on and get started on the lab. We've lost enough days this term that I don't feel too bad about doing that. So we could get started on the lab, or if you don't want to do that, I could start. And by the way, we're not going to do Chapter 21, which is geologic time. Not that it isn't a fascinating subject, but we just don't have time for it. And I wish we had time for atmosphere of the Earth. We really don't. We'll use some of that information when we get into the chapter we will be going to, which is weather and climate. So that's what we'll do next, is weather and climate. So if you do say, I want to continue today, we'll jump to Chapter 23 and do that. But if you do want to at least get started in the lab, I have it prepared. I think I do anyway. I'm pretty sure I do. So we could start on that. If we don't finish, we can finish it next time. But then plan to Tuesday, last 30 minutes, we'll have the test on Chapter 20, Shaping the Earth's Surface. And that's an in-class one. That once you get too spoiled by these take-home. Okay, what you want to do? Lab and we'll just get started on lab. You probably won't have time to finish it. Or I'll get started on 23. Name it and claim it. Lab. I thought maybe you would say that, and I'm not at all disappointed. Okay? I feel like I've talked too long. Okay, so let me, all right. I'm going to pause this for a minute. All All right, I passed out the lab. The lab for today is on topographic maps, which is fairly close to the chapter we're doing. We've been doing in all of them. And you'll need to read the first part, page 345 and more than half of 346. A lot of what you're going to be finding in your questions you'll find on that page and a half or so. Okay? The materials, again, we don't have the soft clay and stuff, so you can just basically ignore the materials part, and you can ignore most of the procedure there. Okay? The results, and this is what I was talking about, you can get from reading that first page and a half. What do topographic maps show? What's the relationship between the closeness of contour lines and steepness of slopes? What happens to contour lines across a valley? And how would a nearly vertical cliff be represented on a contour map? Just about all that you can get from the reading. Okay? Now, that's only 5 points worth. We got 20 points to go. Go to the last page, and that's page 349, and you see it's an invitation to inquiry. So you'll need to go to a computer. If you don't have one in here, we can go to a lab, or you can do this on your own. Does anyone have a computer with them? No. I can go down and see if I can find a lab that we can go to. Do you want me to do that? Or you want to do it on your own? I'll be glad to. If that orientation classroom's free, we can go back down there, 256. You want to do it or not? What's that? Okay. All right. That's where you'll do the next 5 questions. Now, the specific website that's listed here, I think, has changed. I believe one of the last few times we did this, I was told that it's not at University of Texas anymore. So what I would suggest is just do a search for Devil's Tower National Monument, Wyoming. And specifically, I would use shaded relief map and or contour map. Use both of those terms if you know. See what you get. Keep trying until you get it. When you get the contour map, then try to answer these questions. Now, while we're talking about these questions, what would you say the difference between 1 and 3 is? On page 349, the invitation to inquiry, Devil's Tower National Monument, Wyoming. Number 1 says, what is the elevation of Devil's Tower? Number 3 says, what's the approximate height of Devil's Tower? Are those asking the same thing?
The height be from sea level?
No, that's why elevation is from sea level.
Okay.
Height is height above ground level.
Above ground.
Okay. So that's the difference there. Don't think that's the same question. Okay. I'll put your lab over there on your book. You might have to get. What we're going to do is go down to the computer lab if it's free, the orientation lab. But that's only 10 questions. We need 15 more, don't we? So here's what we're going to do. I'll take with us when we go down there our good old Alabama Atlas and Gazetteer. And guess what the subtitle is? Topo maps of the entire state. That means topographic maps. That's what this lab's about. So, the first part, we got 15 more things to do. So the first part is to find where you live. Now, the way this map is done, by the way, if you need help with it, here's the whole state on the back. And these are the page numbers that you'll find these things. And the page numbers always go across 2 pages. Okay? very first one here is 1617. 1617. So the first thing you do, the first one I want you to do is to find where you live. Find the pages where you live. And I'll give you a hint. I bet you most of you, if not all of you, live on pages 30 and 31. Those pages there. Okay, and then what I want you to do, here's what you'll do. I'd say maybe on the back page of that, it's a white page, right? Or if you want to do your own paper, you can do that. First thing you do is put down the page number. And for you, it'll be the page where you live. That could be 30 and 31 or what. Okay? And then what I want you to find is a feature on this figure where the topographic lines, they call them isoclines, are close together. The contour lines are close together. And there's bunches on here. Find the feature that where the lines are close together. So put the page number first, and then a feature where the lines are close together. Okay? And then tell me what that means. What does it mean for the lines to be close together? It's one of the questions on your thing. It's one of the reading you'll do. Hopefully you'll see that. If you have doubts about it, ask me. Okay? So that's the first thing is page number. Second page is a feature where they're close together. Third, what does that mean for them to be close together? Fourth, where they're far apart, where you don't see any topographic contour lines. And you may have to really look to find those, okay? But find something where a feature, a town, or something that the lines seem to be far apart. And when you find that, you'll list that, and then what does that mean for them to be far apart? So that's 5 items. Page numbers, and there'll always be 2, 30, 31, or something like that. Feature where the lines are close together, what does that indicate? Feature where the lines are far apart, what does that indicate? Okay? And then you pick any other 2 pages anywhere in the state and do at least 3 pairs like that. 30, 31, 14, 15, 18, 19, 44, 45, wherever. But pick a total of 3 of those. You have 5 things listed on each one, there's your other 50 points. If you want to do an extra 1 or 2, just because they're that much fun, or you want to make sure you're getting things right, you might do that. So that way, if you miss something somewhere else, you can get enough points to still reach your 45. Okay? So I'll carry this with me, and yeah.
I'm sorry, I blinked out. I got 3.
Page number. Page numbers. What does that mean? What does it mean for them to be close together? And for a feature where they're far apart, what does that mean? So that's 5. And by the way, what does it mean? It's going to be the same for every page you go through those. Drill that into your head. All right. While y'all are working on the first part, I'm going to go down and see if the room is open. So I'm going to pause this again.